Okay, let's go. So this is my research seminar. Okay, who's heard of nerd sniping? Anyone put their hand up? Anyone actually heard of this term before? Okay, I'm going to have to explain it then. So there's a type of person that if you show them an interesting problem, they immediately lose the ability to think about anything else, and they'll just start working on that interesting problem. So in this example, there's a physicist crossing the street, and you show them an interesting problem, and he immediately freezes to try and solve it and gets hit by a truck. What they say is that the physicist is 2 points, the mathematician is 3. I have a physics degree and a maths degree. I'm very susceptible to nerd sniping. And for that reason, I don't really have a singular research theme or a coherent theme that I'm going to talk about in this presentation, because as some of you probably have realized, I'll just work on anything if you've got some interesting data. So for that reason, this presentation has sort of 3 bits to it. And because Min is an apology, I'll probably use the whole time, so just stuck with me. So the 3 projects I'll be talking about, one is called How Do Runners Run? Data from the trail cohort. The second theme I'll talk about is multimodal video and sensor data sets. And the third one is more of a performance analysis type problem in Australian football, but using a causal inference approach. So these are 3 projects that sort of do a reasonable job of covering the kinds of things I've been working on in the last few years. And there'll be some people in the room that have seen 1 or 2 of these, but I don't think anyone will have seen all 3. So hopefully there's something interesting for everyone. Okay, so runners. Hands up in the room if you're a runner, or you would call yourself a recreational runner, not a competitive runner. Yeah, quite a lot of people here think they are runners. Well, you are runners, that's the definition. Who uses a watch to track their runs? Yeah, any runner who doesn't use a watch? Wow, it's rare. Very rare. Okay, would you ever stop a run, assuming you can run that far, at 41 Ks? Yeah. I knew you'd say yes. Yep.
Haven't you got 200 more meters to go? That's 42.2.
Oh, that's what I mean. Who would stop short of a marathon, like just run another block, or once around the block and you run the marathon? I know, yeah.
You run 41, you run 42.
What about for the less serious runners? Would you stop like 500 meters short of a 10K? You would. Okay. Well, the data says otherwise. How do you think you compare to other recreational runners? So I'll show you some data here that will let you see where you sit on the spectrum. Okay, so the trail cohort is a big study that is sort of centered in Latham. I'm going to go through this stuff very quickly, but they recruited recreational runners, so self-reported recreational runners, with and without a history of knee surgery. And they've taken lots of data on them at baseline, so they've asked them lots of questions about their beliefs around running, what their life is like. They've taken knee structural features, so imaging data. They've got 3D running biomechanics in the lab. And the primary outcome of this study is looking at changes in knee structural features, stuff that I can't really explain. But in the middle, all of these runners were given or use their own watches, and we get access to all of their running data for a period of 4 years. It's now going to maybe be up to 10 years, I think, yeah. So I'm going to show you some data from 2020 to 2024, so a 4-year period. So the data is going straight from their Garmin accounts into our database directly via an API, so it's not relying on them clicking anything, it just comes straight through. So as long as they're wearing the right watch when they run, we get the data. And the research questions I've been looking at are, what are the behaviors of this cohort with respect to some of the typical running parameters around frequency, distance, pace, cadence? How do these differ by group? Because we have surgical group and a control group, also men and women. How can the runs and runners be represented? So this is a really large quantity of data. We need to sort of characterize them in some way to do any sort of meaningful analysis of how this running behaviors potentially influence the outcome variables and things around load accumulation as well. So how many runs and runners have we got so far? So 228 runners have performed a bit over 100,000 runs with a median runs per person of over 400. So that's quite a lot. And we have a lot in each of the sort of subpopulations here, men, women, and surgical control as well. So like, tens of thousands of runs for each subpopulation. In total, it's over 1 million kilometers, but 11 years of running in that 4-year period. And there's more being collected right now. Like there's probably 20 or 30 trail runners running today. And we get a really rich picture of what these people are doing. So this is the timeline over those 4 years. Each dot is a run. This is 3 people. The size of the dot is the distance of the run, and the y-axis is what time of day they started. So 192 used to run in the afternoon, but now just loves to do a 5K at 8 a.m. every day, basically. 270 is much more variable. They run mornings and arvos, sort of middle of the day, lots of different sized dots. 308 used to run in the afternoon and then switched to being a morning runner. So you see sort of this rich picture of how these people are running. Okay, so when do we think? Let's take some guessing. So do we think there's a preference? What day, like a day of the week preference, or is it going to be flat? Sunday's the running day. The day you go for a run. Tuesday. Well, Tuesday, Saturday, Sunday, just not Monday. Yep.
Because you're recovering for Sunday.
Yes. Time of the day, as you saw, it's quite bimodal. So you run in the morning, like before work or after work, and then lunchtime runners as well. But it's quite smeared out throughout the day. We even have some like weird instances of people running over, like starting before midnight and finishing the run at like 1 a.m. and that really messes like duration of run calculations in my code. So there is some evidence of day week preferences and the general morning preference in the cohort. We can look at the differences between men and women there, actually quite similar. This is just some like curiosity stuff to have a look at. I found this kind of interesting. But the main analysis we did for this first study was we looked at sort of 4 run characteristics or runner characteristics: frequency, distance, pace, cadence. Okay, so let's look at frequency first. So the most common gap between runs was 0 days. So these are recreational, self-selected recreational runners that actually like to run like every day. So yeah, that was the most common gap. That's the distribution of gap lengths between runs, very skewed obviously. But if you then aggregate by week and you look at the number of runs per week, we see actually the most common median number of runs per week is about 2 or 3. So there's a disconnect there, right? If the most common gap was 0 days, we should see more people up at the 6 and 7, right? So it seems a bit strange. So this highlights why we need models that account for repeated measures. Because if we have a model that accounts for repeated measures and look at this data, what happens is we see massive between-person variation. So some individuals are running like every day, and just because they run every day, more of their data is in the data. So the data is skewed so that it looks like these extreme runners that run all the time. And that's why you see the disconnect between just sort of summary statistics versus modeling and accounting differences. So I'll show a few of these types of graph where the solid points down here are the subgroup means, and then the lighter dots are the individual participant means. So there's 228 of them. What we see is the common story. We see very large between-person variability, right? So the people are quite different. We see quite high within-person correlation. So if you are a high-frequency runner, that's sort of like, so if we observe you running like with very small gaps, you tend to do that again and again and again, right? Pretty insignificant gender-based differences, and the surgical group ran a little bit less frequency, but like not major differences at the subgroup level. The big takeaway from this is that it's all governed by the individual preferences, right? and then you see this phenomenon, which is that a small number of high frequency runners dominate the data if you don't account for it in the model. If we look at distance, you see this weird type of distribution that one of the weirder ones I've ever come across. So this is the distribution of distances with spikes at all of your distance milestones. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10K milestones. So people run and then they stop their watch at exactly like, oh, I finally get to 10Ks, I'll stop. Well, that's how I feel. Well, finally got to 3Ks, I'll stop and go home. So we see again, but it's very long tail. See a little blip here. That's your marathon distance. But a lot of people are running between like sort of 6 to 12Ks per run. If you look at the median weekly distance, that's more like well, it's massive range. So 8Ks a week. So the median of the medians is about 30K a week. But there's some people doing up sort of over 100K a week average running distances. Again, it's the same story. See massive between person variability, all the way from sort of on average you run a 2K up to your normal run is more like 12 to 15K, high within person correlation, and not very large group level differences. Sort of just the shortest run distances were seen on average in the surgical women. Pace is much more smoothly distributed because it can't be sort of controlled as fine-grained as distance. Again, massive between person variability. You do see a reasonable sex difference in pace on average. So again, yeah, the males do on average run faster, but there's plenty of overlap in these distributions. You can find individual women who run faster than plenty of the males, right? So yes, there are group level differences, but again, I'll stress the dominant factor in all of this is the individual preferences. Similar story for cadence, or even more similar for cadence. So what does this mean? This was one of the first pieces of analysis we've done on this data. The individual runner tendencies or preferences were the biggest effect in all models. And the group average doesn't represent the individual here. For example, the largest subgroup difference when you're looking at distance is surgical women, which was the lowest, versus control men, which was the highest. That's the largest group-based difference, but you can find multiple examples of individual women from the surgical group whose typical run is twice as far as a control man, right? So that's that dot versus that dot is the opposite direction as the group means, right? So if you look at sort of the literature in this area of like recreational running cohorts, there's been quite a few of these collected and reported on. They will often just report group, on average men ran faster, on average men ran further. That's it. That's all you get. You don't get the individual variation, like which tells the real story here. I think. You also see correlation between each of these four variables as well. So participant who runs often is also the group that run further, they run faster, and they run with high cadence. So just get this sort of compounding effect of they dominate the data as well. We saw minimal differences between men and women, which is a bit different actually to previous recreational cohorts. That might be a bit of selection bias. A lot of previous data was from survey, not from the actual watches. And I have found some evidence of this general phenomenon of men overestimating their abilities in survey data and women, or conversely, maybe women underestimating. So maybe that's what happened in the survey data. And when you actually use the hard GPS data, it sort of disappears a bit. Or potentially there's a bit of a converging of running behaviours in this Australian cohort. The surgical group ran, on average, less frequency, shorter, slower, and lower cadence runs. And that's something that we're sort of digging into more, the reasons as to why. And that's where leverage the expertise of the other researchers in the trial cohort. Okay, but that is just scratching the surface of this data. So I want to show you a couple of other things that we've been digging into that aren't quite as sort of finished as that analysis. But the other thing we're looking into is, well, one of the other things is run and runner archetypes. So as I said, we have over 200 runners. We're monitoring them for 4 years, and we're trying to figure out like how does the running behavior potentially interact with changes in knee structural features. So that's quite like a high dimensional problem. If you think about it, we have 400 or 500 runs. Like how do we sort of marry this all up? Like no one is exactly the same, but are there types? Are there similar groups? And you can see this if you just start to visualize the data in a few sort of clever ways. So this is a 3D plot of speed, cadence, and distance, where each dot is a run, right? And you've got 3 people here. So you see like the blue person, the red person, and the green person, they don't overlap, right? So the person in green doesn't really do runs for whatever reason. Maybe they can't, maybe they don't want to, runs like the blue person, right? So there is some, well, I guess there's clustering here. This is the within-person correlation and the between-person variability I'm talking about. The people separate apart from each other, but they also show like a lot of type grouping within themselves. So these are maybe 3 different archetypes or 3 types of runner. If you pick another 3 random people, see that in this case, the blue and the red are quite similar in a lot of their runs. So maybe they both belong to the same runner archetype. And green here is an example of a super highly correlated person. Like this is the person that does a 5K on exactly the same route with exactly the same pace every day. Right? So there's some interesting avenues of analysis we could go down there. And there's another example there of what this can look like. So we're interested in, can we create like a finite set of run or runner archetypes to hopefully be useful interpreting the data. So we want to try and understand like how is it being generated. So, you know, hypothetically, do we find a type of runner that ends up being bad for their knee or something, which is probably like going to be pretty hard, but that's sort of the idea. We see that individuals show different and distinct patterns. So one of the ways we're looking into this, the type of analysis we've looked into is something called a Gaussian mixture model. So this is where you have data that maybe looks like this. You've got a histogram that's got multiple peaks, and you think maybe the observations are being generated by more than one process. So thinking about this conceptually, you imagine a person, they have 3 types of run they like to do. They like to do, all right, today I'm short on time, so I'm going to do a short, fast run. Or it's a Sunday afternoon, I'm going to do my long, slow one. Or maybe they also do intervals training as well. And they they will look different in the GPS data, right? They will look different. So this individual person's profile may actually have multiple sort of peaks to it. And this is where you could use a modeling technique like this to try and pull out what are the 3 generating processes, the type 1, type 2, type 3 run. And that gives you this idea of like a fingerprint for each runner. So this is actual data. This is ID 12, whoever that is. And this is like a density of where their runs are likely to sit in a pace versus distance 2D space, right? And you could do it in 4Ds as well, but you can't really look at it that nicely. So you could look at distance, pace, cadence, heart rates in this one, but we're not sure if we're going to use that. So this is like a fingerprint of a runner. Then if we do this for each individual runner, can you sort of compare fingerprints and see to people, okay, this person's distribution kind of looks similar to someone else's. We could do that for runs or runners. And we've sort of looked at both. So for one person, you might get 3 to 4 hills, so likely run types. But if you do it for the whole data set, which we also looked at, you would get more like 25 or 30 run types. So across these 200 people, there's lots of different run types. Then what you can do is for each participant, so each row here, you can represent them by the sort of their frequencies of doing each of the run types. So person 1, 23% of their runs were type 25 runs, right? So that doesn't mean a lot, but they never do a 17 or an 18 type run, versus person 4, they actually quite like doing a type 17 run. So maybe those 2 people aren't similar. But once you have this, right, this is now quite a low dimensional representation of a person. It's just 25 numbers per person. You can then do similarity calculations between all the people. Oh, there's one that I prepared earlier. Yeah, that's just what I explained, the same thing. And so we can get similarity scores or divergence scores for each pairs of runners. And these would be examples of people who are similar. So 318 and 402 are similar, and they're similar in like more than one way. They do these ones down here, which are sort of short, fast, and they do these ones up here, which the pace suggests it's probably like walking or walk running. We have a fair bit of that in the data as well, not just continuous runs. So that approach is able to detect that the way these two people run is similar in sort of quite a rich way, whereas these people are like really different. Okay, that was one thing. Another thing we've looked at and we're going to try and dig into is what I've called the urge to run model. So this is a model of a runner's sort of preferences and desires, if you will. Okay, way over time. Okay, so the data is sequential. So it runs day by day by day. Everyone know where this scene from Chernobyl? Yeah, one of the like great scenes in like science communication history, where he goes through the factors within a reactor, nuclear reactor, that make the reaction go up or go down, and the red card and the blue card, and he explains why the Chernobyl reactor melted down. But what we're interested to do is we're going to try and model what are the drivers and dampers of running behavior in these people. So, you know, if you've gone 3 days since your last run, it's sunny Sunday afternoon, and your knees feel good, and I don't know, like you got nothing else on your calendar, like, can we actually model that? And then you're going to go for a 25K run or something at a high pace, a good pace. Or is there other things we can model? Because these people are actually giving us knee symptom surgery survey data quite regularly about interactions between running load and knee symptoms, and is there a feedback loops there? So we haven't really dug into how we could do this yet, but we're just sort of like interested to go down this this avenue, given the richness of the longitudinal data we have for each person. Okay, that was only using, that's all the summary level stuff. We also have the within run data. So we have 1 Hertz time series from every run as well, so every second. So for example, what I'm talking about there is 2 10K runs from one participant on different days. We have time by sort of second by second data on how fast they're running, cadence. We also have heart rate as well. So you can see here's 2 runs that they finished at 10K, but they get there in different ways. So the run A is faster on average with a less variable pace. Run B is slower on average and it's got some flat bits as well. So maybe they stopped to have a drink or stopped at a traffic light or stopped to talk to someone. If we look at their cadences, when they were actually running, the cadences were similar, but run B has stops in it, or data is corrupted. I'd say most likely it's stopping. If you look at speed, run A has more consistent speed. Run B has fast and slow and stationary intervals. And if you look at heart rate as well, run A's consistent heart rate, it's run B sort of way more variable. So this is even just one person, 2 10K runs accomplished in quite different ways. We also have the elevation. So one of them was downhill, flat, uphill, and the other one was uphill, downhill, and maybe that explains it. So you get quite a lot of data from this as well. So within this is now one person looking at 7 different runs. Another thing we've looked into is, okay, are there running states or modes that a person is sort of attracted to? So like, and I'm sure like some of the experienced runners in the room could probably talk to this. Like, is there a certain pace cadence combination where you can get to and you feel comfortable? And you might have more than one of them if you're an experienced runner. So, for example, like within this one run, this is one run for one person, they spend a lot of time at sort of this mode and a lot of time at this mode, but not much in between. But on this run, they were in between. So it's not super clear. But, and then this is sort of like a 2D heat map of cadence and speed where they spent their time in a particular run. So again, is it possible to then represent a run as time spent in a smaller number of states or modes as a way to, again, we need to compress the dimensionality of this. Like, we can't use this as our input, like it's much too high frequency. We've got to try and summarize this in some clever way. So this is what we're trying to do here. We also have lab data. So we're very interested in integrating, estimating load by some kind of lab-informed person-specific weighting, so that the participants ran through the gate lab. So we've got forces at a few different running speeds. And given we have a lot of information time series of their running speeds, can we actually weight every single point? It's maybe some better estimate of load than just distance. Okay, that's the trail stuff. Multimodal video and sensor data sets, so change of pace. Something else I've been interested in over the last couple of years. So what do I mean when I say multimodal video sensor data sets? Video plus LPS or GPS or IMUs or some other kind of sensor. It doesn't really matter, just more than one. This should look familiar. Turns out this building has a lot of sensors in it. So it's great for collecting these data sets, and cameras are pretty easy to get. There's also lots of cameras in the building. So what can we do with multimodal video and sensor data sets? Why am I interested in this? So I'm going to go through a couple of examples. So data sets we've created. So we created a bunch of multimodal video and sensor data sets in the AFL via a collaboration over a few years with Champion Data. And I don't know when it was, last year or maybe the year before, last year. We created a data set using four of the UBL games that were played here with our men's and women's team. And I'll go through some of the applications of what you can do with this stuff. Okay, so the first data set we created, we realized how useful this is called the footballers and landmarks on the ground, or the FLOG data set. So it's about 80,000 or a bit over 70,000 frames of behind the goals cameras of AFL matches. So this is a camera angle that you don't usually get to see on TV, but this is the camera angle that internally the clubs use for nearly all of their coaching and game analysis stuff, because it gives you a nice zoomed out picture of the game. So we've got a sample of, as I said, about 70,000 frames from 9 games, all at Marvel Stadium. And what we have for every single frame is a box drawn around each player, a label for which team the player is on and who they are. So that's 2.5 million bounding boxes. And the reason we're able to get so many of them, so I didn't go in and draw 2.5 million boxes, is that they're generated from the LPS devices that they're wearing. So we've integrated the video and the sensors together, this multimodal video sensor data. We also have annotations for where the ground marking landmarks are. So the center square, the goal squares and stuff. Because you need that to figure out where the camera's pointing, because the camera moves. So we have like 1 million ground landmark annotations as well. So when you have a data set like that, okay, so remember it was using the LPS to make it, we can then take the LPS away, right, and let the camera move around, and we can train a deep learning model, a computer vision model, to do the player detection for us. So these boxes are now being drawn by the deep learning model, right? And it can also, it's a bit hard to see with the contrast here, but it's also predicting like where the ground landmarks are. So that in combination allows us to do this, sort of flip to a bird's eye view, because we know where the camera is pointing, we know where all the boxes were, so we can sort of apply that perspective transformation, and we get the moving dots without the LPS, right? So this is now, so you train the models with sensor data, and then you take the sensors away, and now you can get the moving dots with them. So the black ones here is the ground truth. So you can see here, like the predictions are like right on top of where the ground truth is, so it's working. But you see it jittering and stuff there a little bit. It's not 100%. You can do cool things like with this. So this is integrating LPS onto video now. So these players were playing on each other after a stoppage. So you could think of like a coaching tool here to probably give the North Melbourne defender a bit of a roasting. Yeah, so that, you know, that this type of thing, like annotating video clips, from what I've been told, is an extremely time-consuming and repetitive task that a lot of people get paid a small amount of money to do in professional sport organizations. You can automate this stuff. I can automate any clip of this game with any players highlighting with like the click of a button, right? And it just spits it out. You can do other interesting things. So when these guys are wearing LPS, so you can get speed estimates. This potentially has sports science applications if you're thinking about, you know, there's lots of analysis of movement demands. If you add the context of what's actually happening in the game and in a very concrete way, because you can just watch it on the video, right? You can watch Ben Brown go for a long runner. And then this is a cool one. So this is a spatial control model. So it's like the color corresponds to which team has players closest to that area on the field. So you can think about like a zone defense or something where you're trying to control space. You can visualize it on the video as well. So this stuff, the spatial control model was some done by some collaborators at VU, but sort of all of their work is just the dots on the grid on the field, yeah, like graphs. With our stuff, we're able to project it onto the ground, and it just becomes so much more interpretable, and I think so much more palatable to players and coaches as well. I don't think they like to look at dots on the field. Okay, that was one data set. The second one was the team ID one. So as I said, for each little box around the players, we've got a label of which team they play for. So yes, you can detect here's a player, but you also want to know who they're playing for. So here's an example where it's meant to be splitting the difference between the Essendon and North players. You can see it's not, like it's only 90% accurate, but this was just a baseline one that we mocked up. But you get the idea of what it's trying to do there. Turns out this is like, you can't just use the colors, because within the boxes, the majority color for every box is green. So they kind of, you have to be clever than that. Okay. Another really interesting data set we made was a tracking one. So instead of just individual frames, we're now looking at sequences. So we had 800 sequences of play where the ground truth is coming from the LPS, right? Because the LPS never forgets who is who. Okay, so it's not going to get confused and switch players. So now you get boxes around each player, but it also has a label on each box. So it tracks the same player through the sequence of play. Now, this is a really challenging computer vision problem in Australian football, because with this particular camera, you see how small the players are. Like if I was to ask a expert human to track who is who, they would probably get lost after a little while because they're so small, they make packs all the time. So it's a really challenging problem. So we had 800 sequences on average of about 30 seconds length. So what can you do with something like this? The motivation for this was to try and improve the quality of player tracking at the GPS venues. So this is a really sort of interesting visual. So this is Perth Stadium. The blue dots you see here are where the GPS units say the players are. That screen doesn't look great, but blue and green doesn't look great. But you see here, there's a dot here, and there's no player within 15 meters or so, or 10 meters or so of that dot. In fact, I don't think there's any blue dots directly under a player. So the GPS has error. Like we all know this, but and we all also, people would know it gets worse in a stadium. So this is an example of a stadium with, for whatever reason, its construction really messes with GPS. So this is quite a bad one. And if we let this play out, you'll see that like they just sort of hover around in space. So where the GPS says the players are, like there's never any players there. They're close-ish, but they're just not there. Right. But the GPS never forgets who's who. Okay. So can we use the computer vision algorithm to tell us, okay, accurately there is a player here, and merge in the GPS to tell us who it is. Here's another visualization of LPS versus GPS error. So this is 4 players simultaneously in the same game that have LPS and GPS on. And you see here, so that the error from LPS to GPS is not, it's not constant. It's not fixed throughout the game. It's always 2 steps behind them or something. It's fidgeting around all around them in different ways. So it's a non-uniform error. Okay, so how can you do this? 3 stages. First step is you get detections. So we need a data set to do that, which we have. You need to calibrate the video, and then you need to transform your GPS to local. That's not hard. So we can do that. That's what I showed in the first example, right? That's where we take a video and we get the moving dots. So after you do that step, you'll get something like this, where you get a bunch of red dots. This is where the computer vision algorithm says there is a player. It has no idea who it is, though. It's just like, here, there is a footballer here. All right. The GPS says Jake Riccardi was here. Okay, so that could be him. It also could be Jordan Roughhead. But we know that there probably wasn't a player there. If the GPS says there's a player here, there probably isn't. The players are most likely where the red dots are, but the IDs going to correspond to where the GPS is. Right? So can we do a clever pairing off of these and sort of match up who's who? So you could try and match on a frame-by-frame basis, and you'll get something. Well, it doesn't work that well because of problems like this. So you've got 2 players here and 2 possible pairings, yeah, and you can't really tell if you only look once. You only look at this single frame. I can't really tell which red dot should be paired to which blue dot. And if you try and do that, it looks something like this. So the lines here are the pairings, and the pairings just jitter all over the place. So this is if you try and do it frame by frame, independent. Then it goes all nutty. Okay, what you need to do instead, though, is stage 2, which is before you do that pairing, you need to try and track the players with the computer vision just for a short sequence of time. So if you can get 10 seconds, right, of tracking, then just by chance, like you very rarely get 2 players running in exactly the same way for more than a couple of seconds. So once you go for longer than a frame, the players all start to look different, and then the matching works much better. So you need to get what we call tracklets. I'll skip that, which is basically instead of just dots, you get little worms of dots. All right. So this is the computer vision algorithm trying to make the player tracks. You see here in a sequence of like 30 seconds, it thinks there's 110 players. Right. So we know it's wrong because a player will run behind someone else, will lose them, then we pick them up again, and it doesn't know it's the same player. It just gives them a new ID. But that's okay because we can use the GPS to correct the IDs. So instead of matching on a dot by matching the dots, you match the worms. So you do a matching of worms like this. So there, over that same time frame, the GPS gives you worms, right? So you just take out this purple worm here, compare it to all the other ones, which ones look most similar, and then you do a bunch of matching like that. Okay, that actually is just a standard computer science problem. It comes up all the time. It's called the assignment problem. You have a bunch of units or people, and you have jobs, and there's a cost associated with doing each job, right? This could be like tradesmen and jobs on a construction site. This could be, that's the only example. Yeah, the idea. You don't have to estimate it. There is a closed form solution. Like we just know the answer to this problem. If you can set up your problem like this, there's just an algorithm that will solve it for you. This worm here is quite clearly matched to Darcy Moore in this case. And you see here, this is like the matching cost. You see for each possible worm 1, you could match it to like 48 players, but in every case, there's a clear best choice, right? And that allows you to sort of take the GPS ID labels, put them on the computer vision one, you put it all together, and what you do is you get an improvement in the quality of GPS by an order of 0.5 meter to 1 meter. And this was like preliminary stuff, right? So there's lots. This was like proof of concept work, which we just ran out of time to complete, but there's lots of points along that pipeline that could be tightened up to try and get that better. So short answer is yes. Long answer, yes, but there's more improvements we can make. We also have an action detection data set. So that's like, can we figure out who's kicking the ball at a given time? Or so a few other steps to that. Is there a ball being kicked at any single frame? Who is kicking it? Where in the frame is the kick happening? So we have a data set, again, where we integrated LPS, video, and manual annotations from Champion Data for that. But we didn't even get time to look at that at all. So creating these data sets is actually like an avenue of research in itself. So this isn't ours, it's someone else. Obviously, it's called Sports MOT. MOT stands for Multi-Object Tracking. So Sports MOT is a data set that was published in 2023. It has basketball, volleyball, football clips in it. In total, 240 clips, and on average, they're not very long, of the order of 500 frames, which is only a couple of, it's like less than 30 seconds. Yeah. We were able to create one of comparable size, like 750 frames on average, 800 videos, and the pipeline just scales up. Like we could just do that for every marble game and get hundreds of thousands of clips. But I couldn't publish any of it because we don't own the footage. This weird political stuff around AFL footage. So what we wanted to do instead was to try and create our own version of this using the facilities we have here. There's another example. SoccerNet is another one published in 2022. Soccer tracking videos. And there's a bunch of other ones in all different sports. So there's soccer player position one. SoccerNet gets published every year. It's a recurring competition. There's other ones like synchronized video, motion capture, force plate data set, large-scale multivariate soccer athlete health performance position monitoring data set. So that, oh, and then this one. This is done by some the Trobe researchers, Stu, when he was here, ASP set sports pose. You want to recognize? Spen Dascombe, yeah. So he's in the paper, and I'm in the data set as well. There's all these videos of me pretending to play soccer and stuff on the field. So yeah, creating these data sets themselves is actually really valuable to the community. Because what happens is you put this up, and then you get computer scientists from all around the world competing on who can come up with the best algorithm, right? That's sort of how this works. And that's why we see like really good progress in computer vision tasks. But no one's done it in Australian football yet. So we tried to do this. We were all set. We had two amateur teams, Fitzroy, and I can't remember who their opponents were. All the players had signed, okay, we're going to wear GPSs. You can release that data, film the games. This was drone footage I collected. We're going to film it with drones. And then it was March 2020. So the game got cancelled and the world got cancelled and everything got cancelled. So we weren't able to do that. What we were able to do a couple of years later, though, was do it with basketball. I would really like to do it with Australian football because no one's done it before. So if we can sort that out again, if anyone's got enough contacts. So we had 4 UBL games out here, 2 of the men's, 2 of the women's games. We filmed them from 4 different camera angles. So we used the inbuilt cameras system. We put a camera on each of the baselines and filmed from the balcony here. All the players wore LPS units, and they've all consented to have the video and data publicly released. So this is what we get for 40 seconds of tracking data from one of the games. We know we can calibrate the cameras because it's our LPS system, so we know where everything is. We know the coordinate system. So what we get is something like this. So this is the LPS data projected onto the video of the game from the start of one of the women's games. So let's let it play out a little bit. So you see, like, LT7 is the Latrobe player wearing singlet 7, and it always knows where they are. It never forgets who they are. The LPS is the ground truth. It's super accurate, which we would expect, given sort of what it is. And even obviously, all of these players are fully occluded by this Latrobe sign, but the LPS doesn't care. It does work on video. We also have, and this is some MSA students. We also have IMUs on them, so we've got accelerometer data as well. So we've got all of this for all of the players for all of those games, except for a couple of players who took the bibs off because they were sooks and they were uncomfortable, which I'm still bitter about. So that there's some holes in the data. So you can do, this is now a computer vision system doing detection and tracking, and you see how bad it is. Like it, switch. It can't keep track of who's who. It's really hard, right? But can we use the, for example, the IMU data to label who is who? Is there enough signal in the accelerometry to figure out who is who? So that's another, a lot of stuff I showed before was video and LPS or video and GPS. This is now video and IMU, which is another problem, sort of a different problem, which has lots of applications because IMUs are will sort of work everywhere. They're high frequency, they're relatively cheap, they're small. Yeah. So I want XY locations with correct IDs. The vector units give this, right? But you know, we get LPS here because we're fortunate. You don't get it anywhere else you go. Don't use GPS inside video is cheap. So can we combine these two? So it's something for the future we can try. But maybe I can't figure this out. I probably can't. But I've got the data. What if we just release it, which we still we will do eventually, and then someone else might figure it out. Yeah. So that's the power of these open data sets problems. All right. I had another one on footy goal kicking using causal inference. I'm going to flick through it really quick because it's kind of interesting. Okay, what would you do next? Or what should the player do next? Pass or take a shot? Okay, so the ball's over here. You let this passage of play out. They're running into goal and freeze. Okay, so if we all follow that, should you? Okay, so who would take a shot or who thinks they should take a shot? Okay, so otherwise everyone else thinks they should pass, yeah? Okay, unselfish group. What about this one? Ball starting in the centre bounce. Freeze frame there. Okay. Who wants to take a shot? Yeah. All right. Cool. In the first one, the player decided to pass. In the second one, they decided to have a shot. But what was the correct decision? That's what we're interested in. So scores per inside 50 in the AFL had been declining. This project done a few years ago. That could be due to rule changes or improved defensive tactics. But what about the attacking decisions? So is there some points being left on the scoreboard by suboptimal decision-making regarding taking a pass or having a shot? So this was working with an industry partner and talking to multiple AFL teams now. This is actually something that they talk about a lot. Turns out this comes up a fair bit in like post-review meetings, and there's sort of lots of intricacies around team dynamics and stuff goes into what the coaches ask the players to do. But it's actually a really good problem space of analyzing a decision because the attacking player is relatively in control in that situation. Like he can choose what to do. It comes up fairly frequently. And it's sort of, a lot of players are in two minds there. Okay, so what we're interested to estimate is the causal effect of choosing to have a shot at goal versus passing on when within a reachable distance from goal. So we want to know the size of that effect. It's positive or negative. So we have to set some definitions. So we use 35 to 60 meters. Okay, so the difficulty here is at the point of decision, two futures could be imagined. So you have some player, they could choose to pass or take a shot. If they choose to take a shot, they could get a goal behind, they could totally miss the goal and have a stoppage, they could turn it over, they could just get a loose ball and then get the crumb. All right, so you have sort of like a spectrum of outcomes. If they pass, they could make the pass, they could turn it over straight away, they could go for a stoppage, and then the player they pass to could take a shot, or they could pass and get these sort of branching futures, right? Only one gets observed. We can't, only one of these paths ever gets observed. So the true causal effect would be if we had a time machine and we could do both, right? And we could compare what happened. But we can't go back in time and directly compare. So that would give us the true causal effect. And we can't just aggregate all passes and shots, because that's just not going to give us an unbiased estimate, because there's a heap of confounding variables. So where the defenders are, scoring the game is, who the player with the ball is, how much time is left, do they have passing options? All of that confounds this relationship, okay? So the match context confounds. So some factors, like having someone opening the goal square, that will cause you more likely decision to pass, and there's a causal influence there, more likely to be a good outcome because someone's opening the goal square, right? So that's a confounding variable. So you've got to try and control for that. So how do we analyze the effectiveness of decisions that were never made?
Come on, get yourself something new.
Do you think so?
You'll love it. Put yourself first for a change.
I guess.
Same age, same income, same starting balance. Whether Lucy switched to an industry super fund 5, 10 or 15 years ago, she's been better off. Compare the pair.
It's not too late, Soph.
Past performance is not a reliable indicator of future performance.
So this isn't a sponsored presentation. That is the crux of causal inference, right? Why do they say same age, same income, same starting balance? Why does that make it a more compelling argument? Right? Because they're trying to argue that the cause of the difference in wealth was the super fund. So if you match everything else and you only change one thing, then that's the cause of the difference, right? So if you at the start one was already had way more money, like then you know people wouldn't believe the ad. So yeah, that's what they're trying to convince you. It's a sort of statsy way of doing this is like something called propensity score matching, where what we're going to try and do is instead of modeling the outcome, we'll model the decision. So what things like pressure, period of play, distance from goal, margin, angle, how do they influence the decision to take a pass or shot? We model this, and then we do a bunch of matching, and then compare the pair with, we look for situations where the context was similar, but the players actually made different decisions. And then we just compare that subset of the data. Okay, yeah, we have data. You see interesting relationships of like angle from goal versus probability of taking a shot is like really extreme, right? If you're on the boundary, you're more likely to pass. Distance to goal is massive, so there's a big drop off at about 50 meters. There's a number of players who just can't kick that far. If you're winning by heaps, your probability of taking a shot goes down because you're just more generous probably, or the team's so good that they've probably got good passing options. Later in the quarter, you're much more likely to just have a shot because players are potentially thinking we're running out of time, right? So you can get quite a good calibrated model for the decisions. Yeah, so you get an example like this. So quarter 2 seconds, you know, blah, 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 blah. You get a propensity of 32% chance of taking a shot. So what you want to do is you want to look for another example in the data with very close, similar propensity score, but the two players did different things. Right. So you have to do this matching procedure, which I'm going to skip over. But yeah, you get something like this. Similar pressure, 21 points up, 23 points up, 52 meters out, 52 meters out, 47 degrees away from goal, 42 degrees away from goal. Blah, 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 blah. Propensity is 45, 45. This player chose to shot, this player chose to pass. So that makes a pair, right? Then we look at the outcome variables for these pairs, do that again and again. So you get lots of pairs. The result is summarize, take a shot more often. In all possible ways of looking at the outcome variable, there was a small but significant non-zero positive effect. So but you got to temper that, right? So this doesn't mean just take a shot all the time, because that will mess up game plans and stuff, right? Like the forwards will stop leading, everyone will hate you. But what it means is, on average, when a player is in sort of two minds, this analysis suggests you could see some benefit from coaching them to just take a shot, just take a shot. And the reason is you're more likely to just kick a point than turn it over directly. Right? If you're in two minds and you try and pass it, you're much more likely to turn it over. If you're in two minds, take a shot. At least you get a point. Right? And in modern AFL, defenses are so good that getting a point is actually worth about 1.2 points because you're in a positive field equity position. The ball stays down your end. Yeah, there's plenty of other ways we could extend this, including using player level effects. Okay, that was lots of stuff. Hopefully you found it interesting. I put this on every slide. You can read it and maybe laugh. Stats are fast. I don't have any answers for questions.